Greetings, welcome to lecture number 34 on basic RLC circuits. I am Razavi. Today we will continue to look at the natural response of the series RLC circuit, and in particular look at the voltage on the capacitor as a function of time. And that wraps up the natural response of the circuit. And now we are ready to go and look at the driven response of the circuit, meaning when we have an explicit input. And to get there, first we'll make a note on differential equations from first order and second order, just to understand certain aspects of these equations. And then we will jump into the driven circuit topology and try to derive its response. Now, before we go there, let's see what we have learned about the circuit so far. So here's our series combination starting with a voltage on the capacitor and a zero initial condition in the inductor. We wrote the differential equation and it looked like this. And we have two initial conditions. So this current is zero and the initial voltage on the capacitor translated to this expression for the derivative of the current at time zero. So now this differential equation in terms of I1 and these two initial conditions in terms of I1 can give us the solutions that we are looking for. And then we wrote the characteristic equation and found the roots. And as usual, it's a second order system. So depending on what we have under the square root, we can have an overdamped response if this term is positive, which means R1 is large enough, or we can have a critically damped response if R1 is equal to this value. And we can have an underdamped response if R1 is too small. And here are the plots for this current. It has to start from zero and has to end up in zero because eventually everything dies away and there won't be any energy left in the system. So in the case of overdamped response, the current goes like this. For critically damped response, it settles faster. And for underdamped response, it tries to settle too fast. And as a result, it makes these oscillations before it decays. So today, we would like to find the voltage across the capacitor. Last time, we found the voltage across the inductor. So the voltage across the capacitor is the natural choice at this point. OK, so let's try to find that. So we're going to say cap voltage, and we write the circuit, we draw the circuit quickly. Here's a V0, here's C1, then we have a resistor R1, and then we have an inductor L1, and we have found this current already. We called it I1, right? So we have the current equation, one of those three equations, and then we just need to find the voltage on the capacitor as a function of time. So let's call that voltage something so that we have a symbol for it. And this voltage we will call VC1. So VC1 is equal to V0 at time 0 or 0 plus. And then generally it's a function of time. So we would like to see what it looks like. OK, so before we write equations, let's see intuitively what we expect VC1 to do. Starting from I1, which we had before. So let's say the system is overdamped or critically damped. So I1 as a function of time starts from 0 and then goes back to 0, right? So that's the general behavior that we have. So what do we expect for VC1? Well, VC1 should look like this. At time 0 plus, right here, the voltage is still V0, right? We decided that the voltage on the capacitor cannot change instantaneously. So what we expect is that the voltage here is V0. And then at time infinity, this voltage is gone because all the energy in the system is dissipated in this resistor. So at time infinity, it has to be 0. And in between, somehow it goes from V0 to 0. If it's an overdamped system, we expect that it just goes like this. All right? So that's what we expect, and we just have to find the equation for this behavior. All right, so that should not be that hard. we go back and say, okay, we're looking for the voltage on a capacitor, and we know that the voltage on a capacitor is given by 1 over the capacitance, integral of the current through the capacitance as a function of time, except that we have to be careful with the signs. Here, the current flowing through the capacitor is going from the low terminal to the high terminal, right? This I1 going like this. Whereas the voltage that I have assigned to the capacitor is like this. It has its high potential over here, low potential over here. So the current through the cap is going from low potential to high potential. Therefore, the equation of the capacitor takes a negative sign. So we have a negative sign right here. Okay? All right, so what this says is integrate the current as a function of time, this current here. Then divide by C1 and then multiply by -1. So flip it upside down. And that will be the voltage across the capacitor. So before we write the equations, let's try to follow this prescription and see, qualitatively speaking, what this will get us if we start from here. So this equation says integrate I1. Let's integrate just graphically, right? What does the integral of I1 look like? So we have integral of I1 dt. All right, so before time 0, we have nothing, so that's 0. And then after time 0, we are gradually adding up the area, right? So the area increases and increases and increases, and it probably reaches a constant value. So our guess is that this will go like this, and will probably reach a constant value. Okay? So this is our guess about the integral of this function as a function of time. All right? Okay, so now the equation says divided by C1, so that's just the scaling factor, and then multiply by -1. So this has to be flipped upside down. So this procedure tells us that -1 over C1 integral of I dt will be this waveform here, scaled vertically and then flipped upside down. So it will look like this. Okay? So we followed our understanding of the voltage graphically, and this is what we got. So is this the same as this? No, we have a problem, right? Something is not quite right here. So what did we do wrong? What is wrong here? Is it this equation that's wrong, or is it this prediction that's wrong, right? These two don't match. So at the first glance, we can observe that these two probably differ only by a vertical shift. Meaning that if I shift this up such that this goes above 0, then this and this actually look like each other. So there is some shift missing here, and why is that? What's wrong with this integral that gave us a different answer? This doesn't look correct, right? The voltage on the capacitor should eventually go to 0, not to some constant negative value. All right, well, what we have done wrong is that whenever we integrate, we have to remember about the constant of integration. The constant of integration is not always 0. So we can add that here. More precisely, after we integrate, we have to add the constant of integration. But let's just add it here so that we don't forget, right? So we're going to say, well, actually what we need is some constant of integration here. And we just have to figure out how much that is, right? Our guess is that it can't be 0, right? Because if I just calculate this, I get this, and this doesn't match my prediction. All right, so now we go ahead and calculate. Let's suppose that we have an overdamped situation. So I1 is given by this expression, as we saw before, right? So we say, for example, I1 is equal to A1 e to the S1t. Actually, I need to multiply this by U of t, if you remember from last time. See that the current is 0 before time 0. So let's open a parenthesis here. We say A1 e to the S1t plus A2 e to the S2t, and then the whole thing times u of t. All right, so that is the expression we have for the current as a function of time if the system happens to be overdamped. And we know everything about I1, right? We know A1 and A2 from last time. We know S1 and S2. How did we find A1 and A2? We impressed the initial conditions, remember? So we had these two initial conditions, this one and this one. So from these two, we could find A1 and A2. So I will just write that quickly here. So what we had is at time 0 plus I1 should be 0. So A1 plus A2 is 0. And then the derivative has to be equal to V0 over L1. So that gives us something like this. A1 S1 plus A2 S2 is equal to V0 over L1. Remember that last time we had this equation? Has to be V0 over L1, the derivative of the current at time 0 plus. Okay, so now, so from these we can find A1 and A2, that's fine. All right, so our job is now to integrate this function, as shown here, multiply by all this, and then assume some k, and then try to figure out what k is. So let's go ahead and do that. So we'll say VC1 is equal to minus 1 over C1, and this integral. So integral of this function here. Because we're integrating from 0 onward, this u of t goes out of the picture. So we have A1 over S1 e to the S1t. That's the integral of this guy. And then similarly here, plus A2 over S2 e to the S2t. And then this integral, which is multiplied by minus 1 over C1, needs a k, a constant of integration. And now we have to calculate k. All right, so all of this is known, right? A1, S1, C1, A2, S2, etc. So we just need to find k. All right, so how do I find k? Well, I go and figure out how much VC1 is at a known time. I replace this t with a known time, and then I can find k. What's the best candidate? The best candidate is t at 0 plus, right here, because we know that the voltage on the cap at 0 plus still has to be V0. So at 0 plus, this is what we have. So at t equals 0 plus, this side has to be V0, so that's V0. And then this side, we should just replace t with 0. So minus 1 over C1, A1 over S1, plus A2 over S2, plus k. So that readily gives us the value of k. So k is equal to V0 plus 1 over C1, A1 over S1, plus A2 over S2. All right, and now I just can write VC1 as a nice function of time. So VC1 is this. I just have to replace k with this one here. So VC1 as a function of time is given by minus 1 over C1. All of this, so we have A1 over S1 e to the S1t plus A2 over S2 e to the S2t, and then we have k, which is this value here, so plus V0 plus 1 over C1 A1 over S1 plus A2 over S2. All right, that is the overall expression for the voltage across the capacitor. Does this take u of t? No, because the voltage on the cap before time 0 is not 0 in this case, right? Because we started with some initial condition. So in fact, it's more like this, right? So all we know is that this is true for t greater than 0. What's happening before time 0, we don't really know, right, for that voltage. Okay, all right, so we have the voltage as a function of time. But there is one little point here that we have to be careful about. We know that this voltage assumes a value of V0 at time 0 plus, because that's how we found K and replaced it here. But does it also agree with our prediction that at time infinity it will be 0? Well, we have to see. We have to go back into this equation and say, how much is this when t is infinity? So we say at t equals infinity. So these are negative powers, so they all go to 0. And we have this expression. So we have Vc1 is equal to V0 plus 1 over C1, A1 over S1 plus A2 over S2. The question is this 0? Right? It should be 0, right? It should agree with our prediction. So yes, the answer is it is. It takes a bit of algebra to prove that. You're going to start from here and here. So here we have A1 and A2. We can find them, right? And then we also have equations for S1 and S2. Remember? The roots of the polynomial. So if you go back and replace A1 and A2 from here, and replace S1 and S2 from the roots of the polynomial, and you simplify, you will see that yes, the answer is 0. So that's okay. All right, so by now we understand how these two are made to agree with each other, right? What happens is that this expression by itself is not correct. When we add to it this constant k, then it gets shifted up. And when it gets shifted up, this point comes to V0. This point goes right above 0, and then the result looks like this one. All right, so everything checks out. We are good to go. All right, so that is one method of finding the voltage across the capacitor. Now, there's another method of finding that. So let's just take a brief look at that. So we'll say alternative method. And the reason we do all of these things is that we want to develop our skills. We want to be able to write equations quickly under any situation. We don't want to have a rigid mind in terms of how we go about analyzing these circuits. All right, the alternative method would be, okay, let's assume we don't know I1, right? We found I1 before, let's say we don't know I1. So I just have the circuit without this, and I'm told, please go ahead and find this voltage as a function of time, all right? So we start from scratch, we write everything in terms of Vc1, and then see what happens. So let's go ahead and do that. So we say, find Vc1 directly, right, without a knowledge of I1. All right, so how do we do that exactly? Well, so all of the parameters in the circuit have to be written in terms of Vc1. So how much is the current through C1? This time I have to be careful with my signs, so let's go ahead and change the color. Let's pick the current through C1 like this. Is that okay? So the question is, how much is that current? Well, the current is going from top to bottom, going from the high end of Vc1 to the low end. So it will be just C1 dVc1 over dt, just a standard capacitor equation. So I will say that current through C1 is just given by C1 dVc1 over dt. And the important point is that the direction is this way, right, pointing downward. All right, so we found the current in terms of Vc1. Now this current continues to flow, so it's flowing this way, it's flowing this way, it's flowing this way, it's flowing this way, right? Circulating this way, opposite of what we had assumed for I1 before. Well, that's perfectly fine. Okay, Now let's turn our attention to the voltage on R1. How much is that voltage? R1 times the current. The current is known. C1 dVc1 over dt. So we write voltage on R1 is R1 times the current through it, C1 dVc1 over dt. But I would like to make sure that the polarity of the voltage that I have selected for R1 is correct. So which way should it be? So I have a voltage across here. I want to put positive and negative on the two sides. How do I do that? Well, because the current is going from right to left, the voltage should be like so. The current always goes from high potential to low potential if I want to use Ohm's law directly with a positive sign, and that's what I've done, right? The current times the resistance with the positive sign. So the voltage on the resistor is equal to R1C1 dVc1 over dt, and it has its positive end here, its negative end here. All right? Okay. Now we go to the inductor. How about the voltage across the inductor? All right, the inductor carries a current like this. So I say voltage on L1. So we know that the voltage across an inductor is just L1 di over dt, right? So the current through the inductor is the current the same as through the capacitor. So that's C1 dVc1 over dt. All right, so I wrote the voltage across the inductor as L di over dt. And we know that when we write that equation, the assumption is that the current goes from high potential to low potential. So that means that the potential across all L1 should be like this, plus here, minus here, because the current has to go from high potential to low potential. All right? So you can see that we face this business of signs of these equations over and over again, and we just have to get this and we have to be comfortable with it. All right, so I have found the voltages across these three devices in terms of VC1. Now I can go ahead and write a KVL around the entire loop. So let's write a KVL in this form. Okay, where do I begin? Anywhere is fine. Let's begin from here. We say we're going up the potential, so we write plus VC1. We're going up the potential, so plus R1 C1 dVc1 over dt. And we're going up the potential, so again, plus this expression here, so L1 C1, the second derivative of VC1 with respect to time. These three voltages have to add up to 0. So here's what we got. All right, congratulations. We have found a differential equation in terms of VC1. So we can find VC1. It's a second order system, so again, one of these three responses should work there. Okay, but we just have to be careful about the initial conditions, right? To solve this equation, we need two initial conditions. All right, so we know that VC1 at time 0 plus is equal to V0, right? This voltage is V0, so that's great. But we need one more initial condition. And for that, we always have to go to a storage element. In this case, the inductor, right? We have one storage element here, one storage element here. So we go to the inductor and we say that, okay, what we know is that the current through the inductor at time 0 plus is 0. Somehow we have to recast that expression in the form of VC1, right? So what we know is that IL1 at 0 plus is equal to 0, okay? But I am interested in something equivalent to this in terms of VC1, not in terms of IL1, because my unknown here is VC1. Okay, so how do we go about doing that? Well, we say the current through the inductor is 0 at 0 plus, right? So what I could say is that if the current through the inductor is 0 at 0 plus, then the current through the capacitor is also 0 at 0 plus. Do you agree? It's the same current flowing through the loop. So if this guy doesn't allow any current, then neither of these devices will have a current through it. So that says that IC1 at time 0 plus must be 0 because these three devices are in series. They have the same current. And then IC1 has an expression, right? So I can say that's C1 dVC1 over dt at 0 plus. That has to be 0. Right? CdV over dt is the current through the capacitor, and that current evaluated at time 0 plus is 0. So now we have an expression for dVc1 over dt, which is 0 plus, at 0 plus. So this expression and this expression allow us to solve this differential equation. So again, Vc1 would have one of these three forms, depending on the roots of this, the characteristic equation. And based on that, we can find A1 and A2 using this initial condition and this initial condition. All right? So I won't bother with the remaining details, but this would be the procedure for finding Vc1 without a knowledge of the current that flows through the entire loop. Okay, very good. So these were some basic notations here, basic understandings that we have developed. All right, so I think at this point it's good to look at the properties of the parallel RLC circuit and the series RLC circuit in the case of natural response, so when we don't have an input, right, with some initial condition. So we have seen that both satisfy second order differential equations, but there are some subtle differences between the two. So it's good to summarize all of this, understand it once and for all, so that the distinctions are clear in our mind. All right, so let's try to do that here. I hope everything fits here. So we say summary of parallel and series RLC circuits. All right, so let's change the color. Okay, so here's the situation that we have. We will draw a line here. So this will be parallel. So we have a cap, an inductor, a resistor. And here we have a cap and a resistor, inductor, or inductor and resistor. Doesn't matter, right? So these are parallel, these are series. And we want to summarize the properties. Okay, so the differential equations are a little different, right? So we saw that in this case, we could write something like this. It was d squared. So for example, I'm interested in this voltage here, right? So similarly, this voltage. So here we said that it was d squared v over dt squared plus 1 over r1 c1 dv over dt plus 1 over L1 C1 V is equal to 0. That is the differential equation we found for this circuit. All right? How about the series combination? So again, if, let's say, this voltage is of interest, right, this voltage here. So we saw that it was similar, except that these numbers change a little bit. So we had something like this, so that... let me see here, or we can just find it from here. See that we can divide by L1 C1. So we have d squared V over dt squared plus L R1 over L1 dV over dt plus 1 over L1 C1 V is equal to 0. All right. Okay, so we see that they are very similar, except that the time constant, if you want to call it, in this case is R1 C1, whereas in this case is L1 over R1, right? That's the main difference between the two. Otherwise, the other terms are similar. Okay, so from here we were able to find the characteristic equation and then the roots. So the roots are like this. So we have S12. Here we have minus 1 over 2 R1 C1 plus minus. Okay, I need a factor of 2 here. So we have a factor of 2, then root of this squared, the 1 over R1 squared, C1 squared, minus 4 over L1 C1. Right, because this is as the coefficient of 1. All right, and we decided that the way this term under the square root becomes positive or 0 or negative, it just depends on how R1 compares to 1/2 of square root of L1 over C1. Now when we write the roots for this case, for the series case, the situation is a little different. So in this case we have S12 is equal to minus this guy here, R1 over 2L1 plus minus 1/2 root of this squared. So R1 squared over L1 squared minus 4 over L1 C1. All right? Okay. So now we have three cases: overdamped, critically damped, underdamped. So we'll have to distinguish those cases. So let me change the color of my pen here. Okay, so we say we have overdamped. We have an overdamped response. For this guy, it has to be such that this is positive, and that turned out to be R1 has to be small enough so that it kills the oscillation. So R1 has to be less than 1/2 of root L1 over C1. All right? On the other hand, here, this resistor has to be large enough so that it doesn't allow the energy to go back and forth between these two. So in that case, R1 has to be greater than 1/2 of root L1 over C1. All right, and again, if you remember, anytime you're confused about these two, you go to an extreme case. Here, the extreme case would be this resistor is infinity. We have an ideal LC tank. Here, the extreme case would be this resistor is 0. So again, we have an ideal LC tank. All right, so then a critically damped response. So critically damped would be simply the threshold value, so to speak. So R1 is equal to 1/2 of root of L1 over C1. And similarly here. So interestingly, both of them have a critically damped response when this condition holds. All right. So it's interesting that whether this resistor is in parallel or in series, the two have a critically damped response in this case. And then finally, for underdamped, we have to look for a case where the circuit tends to oscillate because it's a little too fast, so to speak, right? So in this case, if this resistor is large enough, we are approaching an ideal LC tank. So R1 is greater than 1/2 of root of L1 over C1. In this case, this approaches an LC tank if R1 is small enough. So in this case, we have R1 is less than 1/2 of root of L1 over C1. All right, so that is the difference between the two systems. Okay, beyond that, we saw that the responses were similar. Let's see if there's anything else that would be interesting to note here. All right. And of course, when we write the case for underdamped response, this alpha has a different equation for the two cases, right? So you can see that in this case, alpha would be this. whereas in this case alpha is this, right? So they have different values. And then similarly for omega 1 is obtained by swapping these two, and then this whole thing would be omega 1. And again, you swapping these two, this whole thing would be omega 1. See that the two omega 1s are not the same. They have different expressions. All right, so this is a quick summary of parallel and series RLC circuits. For their natural response, we had only initial condition on the cap, and we let go, and we saw that this is what the circuit does. All right, so in our next phase of studies, we want to look at the driven response of the circuit, meaning there's an input, maybe a step, maybe an impulse somewhere, and we'd like to see what the circuit does. So to get there, I would like to make a few notes about differential equations based on what we've seen in the past and some new observations that are very helpful when we are dealing with the driven response of circuits. So let's go ahead and do that. It's a note on differential equations. So you remember what we did for first order equations? So we saw that it would be something like this, right? So it would be dy over dt plus, let's just call this alpha y, is equal to a constant, maybe beta, right? If we have a first order system and it has an explicit input, for example, a step or a constant value, then this has to be a constant value, right? Past times 0. All right, and there's an interesting projection that we can make here. How much is y of t at time infinity from this equation? So y at time infinity. All right, so if I know that at time infinity y has reached a constant value, a steady state value that's constant, then I know that this is 0. Right? So that means that y at time infinity is just given by beta over alpha. So we say beta over alpha. Of course, the key point here is if y becomes constant, right? So we are making an assumption that y is constant, and what we know is, if that's true, the infinite value of y is just beta over alpha, because the derivative is 0. So now let's go to the second order differential equation and see what we can say there. Again, when we have an input, so of the form, let's say, step. So for a second order differential equation, second order. So again, let's write something like this. So d squared y over dt squared plus alpha dy over dt plus beta is equal to gamma. Beta y is equal to gamma, right? This is a general expression because if this factor is not 1, we can always divide by that factor to make it 1. So we have a simple situation, and again here this side is not 0 because there's an input of the form of a step, for example, right? Okay, so now again, if y is constant at time infinity, what can we say about the value of y at time infinity? Well, the derivative is 0, the second derivative is 0, so the value of y at time infinity is this constant over this coefficient. So we say that y of infinity is equal to gamma over beta. Again, if y becomes constant. All right? So that's a beautiful result because by looking at differential equation, I can quickly predict my value at infinity. And we'll see why that is useful for solving a second order differential equation. We saw that for a first order before, right? We saw that if I know the value at infinity and value at 0, then the response is always expressed as y of infinity plus y of 0 minus y of infinity times an exponential, right? So we're looking to see if we can do a similar thing for a second order system. All right, so then let's go ahead and look at the second order system, but I also need to make another observation, or rather a reminder, give you a reminder about what capacitors and inductors do. So we have seen that at t equals 0 plus, a capacitor looks like a short circuit if its initial voltage is 0. Is that right? Because we said that assuming there's no infinite current to charge the capacitor, from 0 minus to 0 plus, the voltage on the capacitor cannot change. So if the voltage on the capacitors is assumed to be 0 as an initial condition before time 0, then at 0 plus, also it has to be still 0. And the only device that guarantees a 0 volt difference is a short circuit. So the capacitor acts as a short circuit in that very short time interval. How about the inductor? Well, for the inductor, if the current is 0, then that acts as an open circuit, right? If the current is 0 at time 0 minus, it wants to keep it at that 0 at 0 plus, unless we have an infinite voltage, right? If we don't have an infinite voltage, the current has to be 0. And the only device that guarantees a 0 current is an open circuit. All right, so that's what we can imagine here. And then at time infinity, what can we say? So assuming that if all values become constant, so our circuit is such that everything becomes constant at time infinity, then we know that, for example, the voltage on the cap is constant. So C dV over dt is 0, and that means that the cap acts as an open, right? Because it's only an open that guarantees a 0 current. And then for the inductor, if the current through the inductor becomes constant at time infinity, then LdI over dt is 0, so the voltage across the inductor is 0. And that acts like a short circuit. So we say here, this acts like a short circuit. All right, so these are the things that we have seen over and over again. It's good to remember these, now that we're going to go and study the driven response of a series RLC circuit. Now, we don't have much time today. I will just show you what we mean by driven response, and then next time we'll pick up from here. So, driven response of series RLC circuit. We have an input. The input can be anything we want. Let's say it's a step. So we have a step here of value V1 u of t. So it's 0, and time 0 jumps to V1. And then we have a resistor, an inductor, and a capacitor all in series. And let's say the initial conditions on the capacitor in the inductor are 0. And I would like to analyze the circuit. What should we find? There are lots of things we can find. There's a current that will flow through this loop as a function of time. There's a voltage here that we can find, etc. Right? So any of these will be fine. For example, let's say this is the voltage of interest, and we would like to find it directly. So we can do that, right? We just have to write the differential equation and then figure out all the initial conditions and solve the differential equation. Our prediction is that it's still a second order system, so it still has those three cases of overdamped, critically damped, and underdamped response. All right, so if we were to write this equation, differential equation directly for this, we would start from V out and say, okay, this is the voltage I'm trying to find. And then from there, I can find this current, right? C1 dV out over dt. And this current happens to flow through L1. If I have the current through an inductor, I can find the voltage across the inductor. If I have a current through a resistor, I can find the voltage across the resistor. So I have this voltage, this voltage, this voltage, this voltage. I can write a KVL, and then I have my differential equation. All right, that's what we'll do next time. I will see you.